Hello, everyone. My name is George Nedic, and this will be a brief introduction to esp-serial-flasher. So first off, a little bit about myself. I'm an embedded software engineer at Espressif Systems. I mostly work on embedded projects relating to flashing and debugging. So esp-serial-flasher, esp-USB bridge, esp-flasher stub, and so on. I do some help with esp-ADF tools. And I like to spend my free time exploring ways to modernize embedded software development. Here's an outline of what we're going to be talking about today. First off, what is esp-serial-flasher? Why you might want to use it, how you can use it, how it works, and how you would implement ports for it. esp-serial-flasher is our C library for flashing ESP chips from other MCUs, and what you can use it for is uploading firmware to either flash or RAM of ESP chips. You can read chip info like type, flash size, MAC address, and so on. And you can do this over several hardware interfaces. So right now we support UART, which is most commonly used. It's also used by our desktop tools like ESP tool and ESP flash. And currently we support several ports for it. So you can flash ESP chips from esp-32 microcontrollers, STM32 microcontrollers, Zephyr OS running microcontrollers, Raspberry Pi, and it's also very easy to implement your own ports. And why would you want to do something like this? So if you have an IoT product that has multiple chips and you need a unified over-the-air update method, but you don't want to update every chip individually. So what you might want to do is have one master chip that will also update all the other ones. And this is very easy to do with the esp-serial-flasher. Additionally, if you have ESP chips that you can fit firmware into the RAM, you don't even need to have a flash chip on board for them. You can just have a master MCU upload the firmware to their RAM instead. Another use case that's rather useful is offline programmers. So this is very useful on factory floors or for service technicians that are out in the field. There's no need to have any PCs. There's no need to understand what serial ports are or use any CLI tools. You can just have a device that you hook up the product to, and it reflashes it. One thing we are using the esp-serial-flasher for at Espressif is esp-USB bridge. So this is our flasher and debugger, and we are using esp-serial-flasher for UF2 and UART flashing here. Another use case that we've seen from our users is using it for using esp-serial-flasher to build GUI apps to flash our microcontrollers. So the benefit of this is that you don't have any external dependencies. You can just statically link it into your program. So now that you know what you might use it for, how do we actually use it? First off, you need to obtain it, and you can obtain it from one of two places. Either ESP registry, which is our place where you have where you can pull components for the ESP build system from, or you can get it from GitHub if you're using any other ports. Now we're going to show you a quick example. So what I have here is an esp-32 board connected to an esp-32 S3 board, and the S3 board is acting as a host. It will be flashing the esp-32 board here. We have the esp-32 example open, and you can see here, this is something that you should start with. So this is how your program would look like when you're starting around with esp-serial-flasher. And first off, we changed some pin configuration here to match ours. And this is basically configuration for your port. So this is a port-specific initialization function. And after that, we have some helper functions. So when you're starting out, you can use these, as these will provide a high-level way to do things. However, these are not part of the public API and are just part of the examples. So we are connecting to the target. We are also setting the baud rate that we are going to be switching to after we've established initial connection. Then we're getting the binaries, and you can get binaries in several ways. So you don't need to have the binary on your flash chip. You just need to know the size in advance. However, you can continuously receive the binary from some other source and keep flashing it asynchronously. And then we're flashing all the parts of the ESP firmware. So the second stage bootloader, the partition table, and the app. And if you go into these functions, you will see how the public API is used here. ESP-loader connect, ESP-loader get target, ESP-loader change transmission rate. All of these are our public API functions. And if you walk around, you can also see basically how these are actually used. So first we are connecting to the target, then we are switching the baud rate to a higher baud rate if that's supported. And finally, we are starting to flash the target. So we're using the public API functions again, flash start, and then continually writing blocks of 1 kilobyte using ESP flash write. And if enabled, we are also doing an MD5 check using ESP-loader flash verify. The procedure is very similar for uploading to RAM. So we're going to build this now. First, I'm going to export the ESP IDF SDK. Get into the example folder. The next thing we need to do is to set our host chip. And finally, we're going to build, flash, and monitor. The upload here is taking a bit longer because we have embedded binaries for each of our target chips, but you don't have to do this if you have a need for only one chip. And you can see we connected to the target, changed the transmission rate, loaded the bootloader, then verified that, and also did the same steps for the partition table and the app. And we can do the same thing for the RAM example, for instance. So yeah, you can see it's downloading. It's downloading each, basically each part of the binary into the RAM, and now we're also reading from the slave. So this hello world is coming from the ESP32 board. So you might be wondering how this actually works, and you know what is the underlying what are the underlying principles. The first step that an ESP chip takes when it's actually booting is it goes into the boot ROM. And the boot ROM is responsible for quite a lot of stuff. One of the things it does is it sets up the flash chip, and it also does any flashing if there needs to be. While we are actually while the chip is actually booting, we will notify the chip using a strap pin that we actually want it to stay in the boot ROM and that we want to talk to it. And then there's a serial protocol where we'll talk to the boot ROM, in this case over UART, and execute all the commands we need. Now, for the USB port, for the USB interface, the principle is similar. We just don't need the reset and the strapping pins because all of that will be done over USB. And in the SPI case, we unfortunately can only upload to RAM at the moment. And we also need more pins. However, what we get here is much higher speed. And one of the recent advancement we've added to esp-serial-flasher is support for the flasher stub. So because over time, when new chips get released, sometimes the boot ROM functionality changes, or there are bugs that need to be fixed, or there are actually additional features that need to be retrofitted to old chips. We have an approach where we have a binary that we upload into RAM of the target, and then we talk to that instead of the boot ROM. And for example, ESP-Tool and ESP-Flash are utilities for desktop PCs are actually using it by default. And now we support it in esp-serial-flasher as well. So what this will do is upload the flasher stub to the RAM and then talk to that. And finally, you might be interested, okay, my chip family is not on the list of supported ones. How would I actually implement? How would I actually use it with esp-serial-flasher? And because of the modular structure of the esp-serial-flasher, is actually very easy to implement new ports. And we call this platform support packages, we call them ports. So all you need to do is implement a couple of functions and basically configure the build system to use that one. One function that is an exception is loader port SPI set chip select, which is the one you actually only need for SPI. So we are using CMake by default. We're using CMake for esp-serial-flasher as a build system. And if you're using CMake, all you have to do is this. But if you're using a custom build system, then you have to actually find a way to link the port to the library. So all you have to do is link the archive with those functions to the esp-serial-flasher library. And here we're going to take a look at the ESP32 port and as an example. So what we have here is what we saw already, the port initialization, and there is no API restrictions on this. You can make any signature, you can use any type of configuration struct to configure your specific hardware. However, and you can see here that we are configuring UART, configuring the GPIO here. We also have the initialization functions, and here we have the functions that we actually have to implement. So it's loader port write, loader port read, enter bootloader, and you can see basically that this is rather straightforward. We are writing to the UART peripheral here, waiting for the transaction to be done, and then we are mapping the error from the HAL. We're mapping the return value from the HAL one to the esp-serial-flasher one. Now, important thing to notice here is that different interfaces will have different signatures for these in the future. So we actually, basically, it's a matrix between ports and interfaces, and you have to implement a port for a specific interface. And you can see that, for example, in the USB port, there's a lot more, for the USB interface and the ESP port, there's a lot more complexity here that you have to deal with. And finally, this is what we will be doing in the future. So what we are going to add next is 16 megabyte and larger flash size support. We actually needed the last thing we talked about, the stub support, the flash stub support for this. Then we're going to explore eFuse reading and writing support, secure download mode, using the SPI interface to download to flash, and encryption support. And finally, thank you for your attention. We'll be taking any questions.